of the things that we consider laws of nature, how specific those laws are. We talked about three-dimensionality. How does that come from the way we are, so to speak? The notion of space is a consequence of our scale. The idea that we can think about an instantaneous state of space is a consequence of the fact that we process information at a certain speed relative to the distances that we typically look at. If we're doing astronomy or interplanetary space travel or something, then it matters. The speed of light matters. And we can't just say, there's a state of space. We have to say a space, in this reference frame with this kind of time delays and all that kind of thing. It is a feature of our scale that we believe in the structure of science is the way it is. And sort of an interesting thought experiment is this thing that originated very early after the sort of formation of the idea of the second law of thermodynamics, the notion of the heat death of the universe. People say, well, the universe is reasonably orderly right now in some sense, but eventually the law of entropy increase says everything will just turn into heat. What does that mean? It means all those molecules that are now bouncing around in these very fairly organized ways, eventually it will be inevitable. And as I say, I think it's a consequence of computational irreducibility that this happens. Eventually, those molecules will be bouncing around in ways that seem to us, from our analysis techniques that we have today, seem to us random. And so, from our point of view, it's a very bad outcome for the universe. There's a heat death. Everything has just turned into heat. However, it's worth realizing that is a consequence of the observers that we are like now. In other words, those molecules in the future, they are the necessary deterministic consequences of everything that's happening in the universe today. And so they encode, because of the reversibility of mechanics and so on, they encode everything that is happening today. But they encode it in this very encrypted way. And because we are observers of the kind we are now, we just say it looks random. It looks encrypted and random. It's kind of all that detail of information that we have today has all been ground down into random heat. But that's a consequence of the fact that we are observers of the kind we are now. In the future, we may very well be observers who can, study individual molecules and do this and that and the other thing. And we will no longer say, these molecules just sort of randomly bouncing around, it's just heat. It's like, this is the most interesting thing in the world, that this molecule, has this correlation with this thing and so on. The biological observer is one that actually can pay attention to all these detailed configurations of molecules in a way that the human observer right now doesn't pay attention to any of those things. We as observers are pretty big in the universe. Now, when we ask how big are we in rulal space, for example, or what I've just described as physical space, in rulal space is really big. And so this question of how big are we relative to the whole rulad, we're really, really, really tiny relative to the whole rulad. We're pretty tiny relative to the whole universe, but we're really tiny relative to the whole rulad. But in terms of physical space, for example, there's a lot of room below us in terms of scale size. And I do think that at different scale sizes, one's kind of what one thinks are important and the laws of physics will be different. If we were the size of planets, we would have a whole different story about space and time. If we were the size of molecules, we would have a whole different story about the nature of heat. These are things that do depend on our physical scale, and maybe some of these things with physical scale are a little bit easier for us to have some projection of imagination of what it would be like to be an observer of that type. I mean, I think the other big one we talked about a little bit earlier is single threads of experience in our minds versus multiple threads of experience. Can we kind of be in some kind of multi-way trance where we're holding in our minds multiple threads of history at the same time? It's not what our normal experience is. And it's hard for us to imagine what it would be like. I mean, for example, if we were having this conversation and we were both kind of operating multi-way minds, it's hard to understand what, that we wouldn't be, insofar as we're having a conversation where there's a flow through time of this idea, that idea, and so on, we go multi-way, it's a very different experience. But by the way, that difficulty in understanding that is the difficulty of distributed computing, is the difficulty of trying to understand how to program in a way where there are many sort of threads happening in parallel. I mean, it's been something where we know kind of very organized ways to do parallel computation, where sort of everything is sort of working the same way or something like that. But understanding how to sort of deal with that in a case where there are sort of many threads of computation, of thinking going on at the same time, is something that has been very difficult for us to deal with. I think some of the things that we're learning from the physics project give us some kind of organizing principles to help us build sort of technological ways to find it easier to think in parallel, so to speak.